Remember, one kip
Fines.
is 1,000 pounds.
Pounds, okay.
Yep.
So that'll give
So
you.
just think of it as,
How did I come up with?
You owe 240,000 divided by 8,000.
Equals 30.
30. Whatever the 30 is. 5.477.
I know that, but how do you get rid of the pounds in that factor?
okay, so, questions on the homework?
B.
Can I resubmit it at a later date?
Yeah, I might have a
Now
resubmittal
noticing
coming
no
after
mistakes.
this, but,
What's that? Have you already turned it in?
yes.
Yeah, just resubmit it.
Turned it in last week. Okay, so on B.
2.1B.
2.1, yeah, thank you. So, on page 51.
Yep.
The allowable compressive bearing capacity of a soil is 8,000 pounds per foot, per square foot. What should the length of a side of a square footing if the total load, including the weight of the footing, is 240 kips? So that would be the F over P, F equals P over A formula.
One second, let me get all this
Yep.
written down here. So, 8 pebbles in them.
I don't know, let's find out.
This is rough.
I felt confident.
I'm not sure about this because how did, it's asking for just that length.
I got this one. What'd you get?
65.
Well,
Pounds per square foot.
Per
Oh,
side.
wait, okay, I think I got it. It can, the pound splits up, cancels itself out when we do that.
yeah, square foot,
So we're left with the square, yeah, we're left with just
30
feet.
square.
Yeah, and then you take the square. 5.47. It cancels.
Okay,
So,
so we have, we want to put in a square footing. Okay.
yep,
We want to apply a total load of 240 kips. And we need our footing to be square, okay?
yeah.
The bearing capacity of our soil is 8,000 pounds per square foot, okay? So, we want to remember the basic form of our equation is F equals P over A, right? So, what do we know about the load? 240 kips. Okay. Do we want to continue working in kips or do we want to convert it?
Convert it.
We convert it to pounds? Okay. 240,000 pounds, right?
Mhm.
Everyone's in agreement? Okay. What do we know about the area?
That's
We
what
know a
we're
lot
figuring
about the
out.
area?
That's what we're figuring
That's what
out.
we're trying to figure out, okay? But we do know something about the area, right?
It's square.
It's a square, okay? Right?
Yep.
And since it's a square, we also know that L will equal W. So this will just equal some number x squared,
Mhm.
okay? So we're getting close.
So that would be,
What do we know about our capacity?
8,000
8,000 what?
pounds per square foot.
8,000 pounds per square foot.
We didn't convert
So we need to get the A alone.
Okay? How do you want to do that?
If you multiply both sides, then divide that 8.
Okay? So you want to rewrite it, x squared feet equals 240,000 pounds divided by
8,000.
8,000 pounds per square foot.
That will take care of the pounds. Those will cancel, correct? Which leaves us with 30,
30 square feet.
and then we square that.
So you think you did it right?
Was that you, that was your process there, Gilkert?
Yeah, I converted to PSI though.
Yeah.
Okay.
But yeah, I got, what's the
So
square root of 35?
5.47 is
Yeah,
the
that's-
square root of,
Something, yeah,
Okay,
it's
so
between 5 and
5.47
6,
feet.
right?
Yeah.
That's what I got,
Oh,
yeah.
that sucks.
okay.
Yeah.
So,
You don't like being between 5 and 6?
yeah,
No, I.
You got 22.
Gotcha.
Son of a.
so if it's kips and case, so I'm good with that, I don't know if you guys are.
There.
That's what I reworked out after talking to Kurt, it made more sense. KSI and kips. Kips is pounds, KSI is,
Yep,
1,000 pounds.
Kips per square inch.
yep, and then 1 KSI equals 1
1,000 pounds.
kips per inch squared equals 1,000 pounds.
Per square inch.
so how did we come up, okay, can we look at C?
See?
Can we look at A, B, C, D?
Well, this is the one where, because it's asking us for a cross-sectional area, and I came up with an area, but this is the one where I don't think I went back and converted mine.
Okay, so steel bar.
Equally close? No. Over your head.
Not so much over my head, but that's just like setting it.
I have a pretty good feeling in
In the right spot.
Yeah.
because I didn't convert anything. You know what I
In the
mean?
right units.
But seeing the K's, I was like, oh, they're already
Like
in
on this one, the mean rush.
big numbers, so I can just work out the
Well,
problem.
it is, but it's just per square inch.
Well, like I said, I think this is before
Yeah,
I realized.
it's not the math. This one's cancel.
No, I wish we could have like at least an indicator with like just the numbers so we know if it's close. You know?
So, has anybody done a lot of work with steel? Know a lot on tensile stress of steel? It's fine if you don't. So, steel, when you're out in the industry, you'll hear people refer to grade of steel, grade 40, grade 60, grade 75. You may hear a little bit of grade 100, but you won't hear grade 100 as much as the others. What we're talking about when we're talking about grade 40, grade 60, grade 75 is the ultimate tensile strength of the material. So grade 60 steel has an ultimate tensile strength of 60,000 PSI, okay? Here we're dealing with grade 40 steel, and we're giving ourselves an allowable unit stress of 20 KSI, so we have our factor of safety of 2, okay? Half of that value keeping us in the elastic range. If we were dealing with grade 75, that would allow us to bump up to 37.5 for our allowable stress. So I know that's a little bit of a sidebar, but that's where these numbers are coming from. Okay, so we're dealing with different types and different grades of steel. Most frequently, you're probably going to be working with grade 60 steel. Okay, so anyway.
Okay, so
Okay, so
we're answering, I believe, for A again. So we're looking for the area, right? Cross-sectional, that's like taking.
yeah, because here you have a stress.
Yep.
Right, here's where we're allowable. Okay, so here we're trying to figure out how to size out the member for the situation that we have. We know the loading, and we know our maximum capacity.
So you have the equation.
Okay,
Yeah, but I think we gotta like make those the big numbers.
so let's take a step back on this.
That might be right.
How do we rewrite this equation so we don't have to do any manipulation of the numbers right off the bat?
A equals P over F.
A equals P over F. Yep. Okay?
P is your force.
P is your force. Yep.
But you would, so for this, you would extend it, right? So it'd be 50,000.
It's up to you. I work with it how you feel comfortable. If you feel comfortable working in kips,
Well, if it's already in KIPS and KSI, we might as well stay there instead of.
Okay. So you can keep it that way, okay.
Yep. Yeah, because remember, and I'm gonna move this down here.
This is,
actually, so I
this,
don't-
Ben, this is where I'm having, I think it's still understanding the relationship between these.
And so, just to get everybody on the same page, for the purpose of the midterm, for these types of problems, do we just want to see it in pounds
No.
to not have to work with kips?
Whatever you
Feel
feel is appropriate.
it's easier.
Okay. Everybody's gonna feel fine tackling kips on the midterm? Okay.
Yeah. That's fine.
50 kips divided by 20 KSI. Right, and that's the same as saying 50 kips divided by 20 kips per inch squared. Right? Everybody good? Everybody's good with that? And this is the equivalent of saying 50,000 pounds divided by 20,000 pounds per square inch. Okay? So what does that tell us our minimum cross-sectional area is? 2.5 square inches. Okay?
Okay.
Can you leave it at that?
Yeah.
So that's just the answer?
For this particular problem,
Because it's asking for the full cross-sectional area.
yep,
So then like going back to the other one, the 30 feet squared,
So it's asking us for a side.
Well, like, cause it's like,
can you just leave it?
Oh,
at
yeah.
20 or
This one,
50,000 divided by 20,000?
we'd have to go one more step.
Okay.
Yep, because here you're asked,
And then the kips can.
what is the total length of the side of the square footing?
So,
why is it 2.5?
And all we had said was that it's between
I thought it
5 and
was
6. I
25,
mean,
so-
that's fine.
Yeah, no.
everybody's good with,
I actually came up
Square
with
rooting,
the first time around.
You said you could,
30.
submit this?
I had it just squared, I just switched to 20.
yeah, absolutely.
But
Absolutely.
you know it's closed now.
Or the-
Oh, is it?
yeah,
You
he had
did
it.
20 divided by 50.
Yeah.
Cause all mine are
4, which is squared.
decimals off, I just have a decimal in the wrong place.
Okay.
Let's, yeah, I'll reopen it until
Yeah. That too.
Thursday before
All my
class.
answers are decimal off.
Okay. Yes.
What do you get for D?
Like 12.
12 by 12.
Is that what you got?
Because what was the area that you got?
115. We have to find a square.
Yeah, I didn't catch it.
Okay, there you go. So you have until Thursday before class starts if you want to resubmit any of this work.
660. What did you get for D, Kurt? What did you get for A? That's
99,000.
270,000.
Yeah. I guess, yeah, it just never.
Okay, any other questions on the homework?
I'm having some difficulties with 2.2 as well. Let me run through one of those.
Yep.
I guess I'm having some problems with all of them, so it doesn't matter to you. I guess I have work done, but I don't know if
Yeah.
it's done.
Well, throw one out and then let's look at it. Which one are you having the most problem with?
B.
Okay. And then, is everybody all right if I get rid of 2.1B?
Yeah. Well, I mean,
All right, so for 2.2B, we have Douglas fir post.
Did we get a different number for a height?
Nominal cross-section area of 8 square inches. Length is 12 foot. And we're axial loaded to 45 kips. We need to determine how much shrinkage under the loading condition. Okay? So, before we jump into this one, let's take a step back. What's the base form of our equation? How do we determine the modulus elasticity? What's that?
Chart.
Are you doing the E one or the change of length one?
Let's not jump to the change of length just yet.
Force over strain.
Force over strain.
Force over strain. Yep. And how could we rewrite our force?
Pressure over area.
And how can we rewrite our strain?
Delta T or L.
Okay. So then we can rewrite that our modulus elasticity equals the load exerted on our body multiplied by the length of that body prior to loading divided by the area, the cross-sectional surface area of that body, that quantity multiplied by the change in length. Okay? So that's where that equation comes from. That's where all these equations are coming from. That's all we're doing. We're just manipulating how we're pressurizing our system and how that's creating deformations. Okay? And then we're simplifying the math to get it into things that it's very easy for us to determine. So, what are we trying to solve for in this particular problem?
Change.
Well, if you
We're
go
trying to
by
solve for our delta L, right? Okay? So, how would you go about isolating delta L to make your calculations easier?
This is pounds per square inch.
Multiply by the delta, divide by the elasticity.
Multiply both sides by your change in length, right? And then divide both sides by the modulus elasticity. Exactly right. Okay, so delta L is going to equal our load times our length of our material multiplied by the divided by the quantity of the modulus elasticity multiplied by the area. Okay? Do we know everything on this side of the equation?
Yes.
We know the load that we're applying, right? We know the length of our material. We know the cross-sectional area, and we can look up our assumed value for our modulus. Okay? So here our load, 45 kips. Our length is 12 feet. And if you want to work in inches, how many inches are you working with?
144.
144. Our modulus elasticity, what is it? 1,150,000?
1.6 million, I thought.
1.6?
well, it gives you a, no, on that first table, no, it's not. You sure?
49.
Oh, yeah, sorry.
49.
1.6.
Douglas for large and other stores for big.
I was taking the
1.6.
compression and adding zeros.
Sorry, Jay.
So it might be 2.6 though, or 2 by 6.
What's our units on our modulus elasticity? PSI, right? Just keep in mind up here, our stress is in PSI, our strain is unitless. Okay? So our modulus elasticity is also in PSI. Okay, and our cross-sectional area,
Which one is this?
2.5.
okay, and that's what I was going to bring up first.
Right, Brian?
For the purposes of this question, We should look up, right? We have to keep in mind, this is a nominal cross-sectional area, okay? So we got to flip to our table in Appendix A and see what the reduction is to our actual cross-sectional area, so we know how that pressure is being applied. Okay, Appendix A, I think it's Table 8 is where your dimensions are for
660.
for structural lumber. Okay. Okay, so a couple things we said this will be 144 inches, right? We'll change that because we're in square inches and PSI down here. What do we want to do with these guys? We have PSI here, we have kips here.
So it goes to pounds.
45,000.
Convert to 45,000 pounds. Okay? From there, it's just plug and chug. Does that make sense to everyone? What's that? What are you looking at here? Keep in mind, when we're talking about structural lumber, we're talking about
7.5.
I use the nominals.
Yeah.
I didn't go.
A nominal?
Yeah, so I use, yeah, exactly.
So what's going to happen if we use the cross-sectional area that we're given? Where's our area located in our equation? It's in the denominator, right? If we increase the number in the denominator, what is that going to do to our overall number? It's going to make it smaller, okay? And could that get us into issues in this type of a problem?
I got something
Yeah.
crazy. So,
But is
You're-
it that much of a problem?
That therein is the rub, right? That's,
Depends how close you are to it.
yep.
So
It's going to depend on how much room we have to wiggle, okay? So that's why it's important to, when we're performing these calculations, in reality, we'd run both of them, right? We want to see. As John said, is it impacting us? Maybe it's not impacting us. If it's not impacting us, then we can use 64 inches everywhere we need to perform that calculation, okay?
Wait, no, 70.
Typically speaking though, if you're trying to figure out your allowable stress, okay, if you're trying to manipulate it through the force that's being applied, I would recommend always figuring out what your actual is, okay, because now you're dealing with capacity. Okay, when we're dealing with sizing, working within an area, we can run both of those calculations and figure out our wiggle room if there's going to be enough issue, but when we're trying to figure out, if we need to figure out capacity, we always want to make sure that we're calculating to the actual dimensions.
So,
We got two.
how does that give us any nominal size lumber? That's what it's asking us to use. The statement itself, what nominal size square timber should be used? So when we work out that equation, it gives us that.
I don't understand.
It's actually,
Oh, you're looking at a different problem.
I thought we were looking at, oh, we're looking at B.
We're looking, well, and we're looking at 2.2 point B, right?
Oh, 2.2?
Yeah.
To get that initial.
Man, that's what
Yeah, so you multiply.
Yeah, Chad.
Where's the chart at for
Multiply
the,
Yeah, how do you put multiply pounds by-
PSI?
For all these guys, 49.
So then you get 49.
The bottom right hand page of 4849. So it's got some selected values for common structural materials.
0.072.
Because I saw the range, but I didn't see the actual.
Yeah.
So on the bottom,
Did it
yeah,
at B?
0.5.
Yep.
But,
2.2 B.
That's
We
hard.
got- we're using
Like
64.
56 or
Yeah.
5.
So that's the only
What
difference.
appendix is that, or where's that?
Appendix A, I think it's table 8. It has your structural lumber.
Okay, so I don't feel bad.
Got it.
Pounds.
Yeah, we have the right equation.
So, let's go over D at 2.1, since I totally just erased.
Okay, hey, let's bring it back together, okay? So, I'm hearing a couple different things going on. I heard over here, what units are we in?
Yes. What do we
What
have?
units should our change in length be in?
Inches.
Should be in inches, right? That's what we're trying to measure. We're trying to measure axially in one dimension, okay? Do we have that? We have pounds and pounds, right? So those cancel. We have per square inch, right? So this is actually in the denominator. So our inches squared canceled. We're left with inches, okay? So dimensionally we're correct, right? So you're not going to have to do any manipulation of these numbers after they come out of plugging in.
Yes.
Does that make sense to everyone? Okay?
Inches squared to the other inches squared.
Sure. What you get for 2.1D?
Did somebody else ask about where did 56.25 come from?
12 by 12.
Oh yeah, Chad, that's what you said.
Yeah.
Yep.
The size of wood you use, but 115 inches squared.
It's 115 squared, so it's 10.75.
Okay.
Oh, because you know what, I think I know why. 115,000
So you need a
Yeah.
12 by
divided by
12.
1,000.
Yeah, it's 115. I got that, and then you square that, it's only 10.75, so I was trying to figure out what.
So if you, like, for that question, if
Yep.
you used, just
But that
your,
10.75 is
you just
square.
took 8 by 8, used 64 instead of that 56, would that
You gotta
mean your
use 12 by
number
12.
is, would you be closer to failure with that number, or would you be having
So
more of like a blanket for
Because
error
that's
or
the next
whatever?
one.
you know?
So
Yeah.
here we're not concerned about failure. Okay, we're not interested in capacity here. We know what our capacity is. We're trying to figure out, as we're applying this load to this structural timber, how much is it going to shrink? Okay, so what we have to think about is what is that going to mean for us in the field? It might mean that if we use 64 instead of the actual cross-sectional area, we might not put in a sufficient amount of joint material. Okay, so we may have an issue with airflow coming in. We may have an airflow issue with water migration.
9 thousandths lower. That's what it is.
So 9,000 is probably not a big issue over one event, okay, but over the course of the lifetime of a building,
Yep,
could end up being problematic.
and if you have multiple of them along,
Correct.
a series.
Yep.
Yeah.
Yep. So. Rush, you wanted to look at something else?
I figured, I was having a hard time figuring out how to
You just
find the
didn't
nominal
convert- It
size.
says you didn't convert your kips right away.
Yeah,
Probably.
it was another one of those. tips.
Go.
I don't want to see kips ever again. I'm done with the kips.
Don't go into civil work.
I won't.
Your civil work, you'll see kips on plans all the
I'm
time.
not doing civil or anything close to engineering because screw your fucking noise.
Okay.
He's got a civil job.
That's like a good thing I just became a civil estimator, huh?
Yeah. Yeah, there you go. Kip
All right.
money, keep it up.
So again, you'll have until Thursday morning when we start to turn in
All right, I need to re-upload this, that's for sure.
that homework.
Yeah.
The last thing we want to look at in chapter 2, we're going to take and move from analysis of a simple beam to analysis of a truss. Okay, and this will pay off for you when we get into our project later on in the semester that you'll be working on. So, first we want to make sure we all know what we're talking about when we're talking about a truss. So what do we have? What are we dealing with when we're talking about a truss?
No idea.
Floor.
It could be a roof.
Here to learn.
Floor.
Could be a flooring element. Okay. Could be it's any sort of span that's supported by something above it, right? Okay. So it's a framework of members. Okay, so arranging a series of triangles all lying in the same plane. Why do we like triangles? Triangles are great for strength. right? So it helps us distribute the load more evenly, okay? So we increase strength. We also decrease buckling. Okay? When we are working with a truss, we have members, we have, poorly draw those things coming together. We have our top chord, and we have our bottom chord. Okay? When we think about, as we're deforming our truss, whether it be from the effects of gravity, whether it be from the effects of the material itself, various loading pressures that we can put on them, typically speaking, what is happening to our bottom chords? Are we putting them into compression or are we putting them into tension?
Tension.
We're going to be putting them into tension, right? As the truss deflects, these members are going to be pulled down. That bottom face is going to experience tensile forces. What about the top chord? What are we going to be doing with that? We're going to be compressing those members, okay? So, what we're going to be interested in as we're looking at a truss is determining what's going on in the members and what's going on at the joints. Okay? We want to make sure that we're setting this thing up in such a manner that we're going to have static equilibrium, right? We aren't going to push our truss along the board. We're not going to push our truss down into the earth. The truss isn't going to come flying off, which would be a pretty amazing sight, but probably not in too great of risk of that. But then we also want to make sure that as we load it, it doesn't flip off its hinges, right? It doesn't pull off of its supports. So in the analysis of doing this, we have to make a few assumptions, okay? Our first assumption are all connections are frictionless. It's what we've been doing up until this point anyway, but we have to make sure that we understand that, because if we have to take into account friction, then we have to know what type of material we're working with and how they're going to interact with each other. Then we have to do things like calculate the bearing area of all the pins, things like that. So it would just make it that we'd never be able to solve the problem. We'd be talking about the problem all day. Okay? We're also going to assume they all members lie in the same plane. Heck. Okay, so there's no z dimension in this thing. Okay, the truss isn't coming out at us. It's not going away from us. It's just running along the board. All right. We are also going to assume all forces are applied at the joints. Okay, so we aren't loading here. We aren't loading here. Okay? Our loading conditions are going to be of this nature, right? Just allows for ease of analysis. We're going to assume self-weight of the material is negligible. That won't always be the case, but with respect to the amount of force that we're going to put on the thing, we're going to assume that we have this incredible composite material that's highly carbon-based and it's super light. We don't have to worry about what the self-weight of that material is, okay? Again, just allowing for ease of calculation. And then we're also going to assume all members are two-force members only, okay? What that means is, as we apply a load at one point on the truss, it's not going to actually rotate any of the members. it's going to be evenly distributed into this member in the X direction, or I shouldn't say evenly. It's going to be distributed in the X and the Y direction. Sometimes it'll be evenly. In this case, when I'm using 45 degrees, kind of poorly, but, okay? All those assumptions make sense to everybody? Seem fair as a starting point? So, what we need to determine is what are our forces in our members and what are the forces in our joints. Okay? So when we think back to the simply supported beam problems that you did in homework 1, that's all that these really are, right? It's just a simple beam, but now it's on steroids, right? We put some other members in there. We're applying forces in different rates, okay? Our equilibrium conditions haven't changed. And what are our equilibrium conditions?
X equals
0, 0,
y
0.
equals 0 and
The sum of all our forces in the X direction equals 0. The sum of all our forces in the Y direction equals 0. And we don't have any rotation, right? All our rotation is balanced out.
So we're not doing moments.
So the sum of all our moments need to equal 0. Okay? So the joints are much easier to calculate, but in actually sizing out a bridge, we're more interested in our members. Because if we know the forces on our members, then we can blow away all those assumptions and actually size this thing out. Okay? So that's what we'll look at. We're not going to get into too great of detail in the method of joints. In fact, we're not even going to go this far because I want us to get into the material. So let's see. Is everybody good with our assumptions and our definition of a truss? Can I erase that and throw up an example?
yes.
Okay. So we'll look at a couple three-member trusses, excuse me, where we'll apply the load in the Y direction on the first example, and then we'll apply the load in the X direction, okay? That's as far as we'll carry our analysis and method of joints. So, our first example, I gotta put myself more space for the point load. So these here. This B, call this C. So we have a roller and we're pinned. Five feet in this dimension, and believe it or not, we have 10 feet in this dimension. And those are also both oral representations of 5 feet, okay? And we'll say that we're applying 1,000 pounds, okay? So, how will we go about solving this? What do we know for sure that we have, based on what we did with simply supported beams?
Well, we know there's a right triangle point, or right angle,
Yeah,
and we know that the angles are 45.
yep. Before we start deconstructing the truss though, what do we know about the reactions?
It must be equal.
They're equal.
They're going to be equal in this case, right? Okay. So, our equilibrium conditions for the truss itself. Are there any forces acting in the X direction? Okay. And then we know that RA plus RB has to equal 1,000.
Question.
Yes, sir.
So, for that, why wouldn't you just write 1,000 for FOI, like where the 0 is? Cause like, or is it because it's between 2 moments? Or not moments, but points? Like the force, the
So,
Y force.
well, because we don't want the Y force equaling 0.
Well, it doesn't equal 1,000.
The sum of our reactions has to equal 1,000 to be at equilibrium.
Okay.
And then we also need to satisfy that our moments have to equal 0. Okay? Now, which reaction would you like to solve for first? Does it matter to anyone?
No.
Yep. So if we look at the moment about A, how are things going to look? How's our 1,000 pound force going to interact on A?
So it'll be,
It's 5 feet away.
yeah, so RA
How is it acting on the
times
bridge?
10.
On the truss? Is it
Oh, it's-
rotating
yeah.
clockwise?
Rotating.
Rotating clockwise, okay, so it's going to have a positive sense.
5.
And remember, with our forces, we're not interested in this distance, right? Because as long as we aren't changing our line of action or our sense, we can move this force however we want. Okay, so we can move this force down to the level of the truss. And now we're 5 feet away. Okay? What about our reaction at B?
Same. It's the same. But it's
But
negative.
it's different force. It's a negative force.
It's going to be doing counterclockwise rotation. How far away is it?
5 feet.
How far away is it from A?
10 feet.
It's 10 feet away, right? Okay, remember, we're looking at what's going on here.
Yep.
Okay? So, if we don't have any movement in our truss, if we walk away from it when we're done constructing and it stays in place, we pat ourselves on the back, and we also know that this equals 0, right? If it doesn't fly off the support right away, we've got equilibrium. Okay, so M sum A equals 0, and that equals,
So why do you put
yep,
MA equals 1,000 times 5 minus RB?
That's
Is MARRA? Are you just labeling that messed up?
so this is the moment about point A.
Okay. So RB isn't the moment B?
That's the magnitude of the force
Okay.
of the reaction at B. Okay? So what does RB equal?
$500.
500.
500 pounds, right?
Yeah. I swear, if I just
Do the algebra.
It's just dividing both sides by 10, right?
Yep.
First we'd add 10 RB,
oh,
right?
So
Then take our 5,000 divided by 10 to 500 pounds. And we like that very much because now that means that RA also equals 500 pounds. Okay?
So,
Otherwise, you just plug it in itself.
Remember those
in that sense, you just assume that it's equal.
physical equation?
Stop there.
R times the total.
That or
And then
Well, now we have equilibrium for the truss,
times the distance.
formula.
right? But we need to know how to size the members. So we need to know what forces are acting on the members, okay? And the way that we're going to solve it is we're going to use the method of joints. So what we'll do is we'll walk through and we'll conduct analysis at each joint and see how are the members acting at each joint, okay? So we know our total overall equilibrium. Is there any particular joint you want to start at, or do you just want to go as we would through the alphabet? A, B, C.
Sure, let's do that.
Okay. Okay. What I would recommend when you're doing these problems is to draw yourself a free body diagram of each condition. Okay, so draw the joint, draw how the forces are interacting with it. Okay. So how many forces are acting on joint A?
2, 3.
3, right? This member is going to carry some sort of load, right? This member will also carry some sort of load. And then the reaction for the truss itself will exert a load on the system. Our X was 0 for the truss. Okay? Keep in mind, now we're no longer dealing with just a simply supported beam. Now we're applying load through these members. As they're deflecting, they're going to deflect in both the X and Y direction. Okay? What do we know about RA?
500 pounds.
Equals 500 pounds.
It's like the force polygon thing.
What's that?
It's like what we're doing before with the force polygon.
It's very similar. We're not going to use a force polygon though. What do we know about member AC?
It's 10 feet long.
It's 10 feet long. And they're 0 pounds.
Do we know that there's 0 pounds?
No.
You can assume. What do we know about member AB?
5 feet.
No.
You don't know how long
I wouldn't assume that it's 5 feet.
Oh.
We don't know much about member AB, do we?
No.
What do we know about the angle between member AB and member AC?
45 degrees.
We know it's 45 degrees. Keep in mind, what is one of the assumptions that we're making about the forces in our members? We can resolve them into how many forces?
2.
Resolve them into 2 forces, right? An X component and a Y component. And because we know about resultants, we know that this force would have to be the same as the resultant, right? That's how we determined resultants. Correct? Okay?
Sure.
So now we just have another equilibrium condition. How many forces do we have acting in the X direction?
1.
We have 2 forces acting in the X direction now, right? Remember, we're resolving any of our member forces that aren't directly in the XY direction so that they are in the XY direction. Okay?
I need
forces are that we need ABX and AC to equal 0.
So then ABY plus ACY.
Or AC, right? Not two ABYs.
Why is there two?
Oh,
Y's?
sorry,
Isn't it RA?
that's RA, right?
Yeah.
Right.
Why?
Says they're both in the Y axis.
Our reaction is operating in the y-axis,
Don't even know why I went up and down. So.
our AB component of our y, right?
Yeah, still trying to get all over that.
RB then?
Way
Why is there
past
an
control
RA
tree.
but not an RB? Or are we just looking at?
Because we're only looking, so we've taken our truss and we've cut it here. Okay, and so we're completely ignoring everything to the right of that portion of the member. Okay?
This is assumed there's no force on your bottom cord, in the X direction?
Nope.
Okay. Or why would there be any Y then? On AC?
Because it's only in the X
Reacting
direction.
with it that
Yep.
way?
Yep. Now, if we're not at equilibrium and there are Y forces acting on AC, what is AC going to do?
Compress.
It's gonna, yeah, it's gonna rotate our truss out of equilibrium.
Sure, okay.
Okay?
ABY has to be 500 pounds, negative 500 pounds.
Okay? Why does ABY have to equal minus 500 pounds?
Because RA equals 500 pounds.
Good, yep. Okay, so we can check that off. What about ABX and AC? Could we solve ABX using ABY? Trigonometry we can, right?
That's 45.
You got an angle, you got a side line,
Yeah.
you got all that good stuff.
We got all we need.
Okay, so John, what would you like to do?
I wasn't volunteering to do it.
Oh, okay.
I don't know.
On the inverse tangent.
Well, you know ABX is,
So how do we know AC then?
10 feet long.
But we're chopping it.
Does the length of our member have anything to do with the magnitude of the force being acted on it?
Nope.
No.
okay,
So we
AC,
don't
we're
know
not
AC.
using AC right now.
so we're trying to find the length of ABX.
For the
We're not trying to find the length,
The force.
we're trying to find the magnitude of the force being acted on it, right? Because once we know the magnitude of the force, then we can size our member appropriately.
you
Don't
tangent
you do
45.
45 over,
No.
Inverse
AB
tangent,
over
45.
tangent of 5. 40. What is it? Tangent. J. Over.
Of X over,
What does this angle have to be?
45 degrees.
That also has to be 45, right? Okay, so what would you like to say?
Tangent 45 degrees equals ABX over negative 500.
Okay? So ABX equals what?
Negative 500 tangent 45.
Yep. What does that equal?
Negative 500 tangent.
Why
There's
did
also
you-
negative 500.
Yeah, so it's negative. I'm getting negative 500. I don't know if I punched it in wrong.
Why is that the case?
That's the equal.
You have an equilateral triangle, right? So those have to be equal to that length. Okay?
So,
So what does-
AC has to be 500 pounds.
AC has to equal 500 pounds. Okay?
Getting close to the end of the math.
Hope so.
So that gives us equilibrium. And now it also allows us to move on to the next, oh, sorry, no, it doesn't allow us to move on to the next joint yet. We have to resolve for force AB, right?
Yeah.
The force that's going, like the,
The force in the member itself,
okay.
right? How do we resolve and determine AB? We could use Pythagorean theorem, yep. Or we could use, John, what do you like using? Oh, you do?
In this case, I think.
Okay.
Law of science. Or you like inverse
I
sine?
think
Inverse sine, is that what you like to use?
Right? We have right angle geometry there. Okay? If we didn't have right angle geometry, what could we use?
Inverse sine.
We could use inverse sine, we could use law of sines. Okay? Worst case scenario, we could use law of cosines. Okay?
Let's do it all. Okay.
So it's what, about,
about 250,000. Oh, that's not right.
wait, what?
That's not
707.
right. My bad.
707, yeah, I was gonna say about 710, right? But 707 pounds? Okay?
Now let's do the other side.
Do you wanna do B first, or do you wanna do C next?
Well, we already did.
707.
C is gonna be the same, right, because of geometry.
What? Oh, because of the angle's the same?
Yeah.
Angles are the same,
Everything's
your member forces are gonna be the same, right? This is still
The
AC.
length is
Right.
still the
Right?
same.
You're transmitting the same load through the system. Okay?
Wow, what a doozy.
That sucks.
So why?
Yeah, it sucks real bad.
Your,
20 questions.
your 5,000 should be 500,000.
Yeah, it's 500,000. Square root of
Oh,
500,000.
He doesn't even assign it.
Yes. That's the rope shot for you.
So on that. real
Thank
quick,
you.
What's up?
What's going on here?
So the 500 square, when you use the Pythagorean theorem, why isn't one of those negative?
So you can't have a negative length.
They would be. Well, what happens when you
When you
square a
square it.
negative?
Becomes positive.
Negative.
Yeah, I got you. I was just wondering.
Positive.
Where are you getting that
Yeah.
No. No, that's also a good point, Rush. Yep. So we should take that into account.
So I'm making note that this is way
So do we have everything?
literally studied this for a week and now.
Okay, so what's our force in this member? AC,
500.
500 pounds. What's our force in member AB?
707.
707. What's our force in member BC?
707.
Okay, so we're good with all our members, all right? So this guy is solved. Let's look at the case where we apply a load in the horizontal direction. Okay, so we're applying a load in the X direction.
It's a little excessive. You can chop it up a bit, but yeah. Did- Just wait and see if you can take calculus.
Oh, good.
Questions there.
Don't say that word.
That one,
Should we take like calculus for reread?
No, I mean.
Calculus for reads.
Not doing that. That's what Gillian
It might be
did
a
for
degree
her.
somewhere.
It is,
Wow.
really
Really?
a bachelor's.
Come on,
That's
bud.
what scares me.
They couldn't pay me to do this.
It's all